So last time I explained the proof of the cone theorem, but I didn't quite get to the existence of contractions. So I just want to start off today explaining some existence of contractions results. So let's let R inside the Kleiman-Mori cone be a KF negative extremal ray. And I guess maybe I want to remark that here we're assuming that X is a threefold, just to remember, so it's a projective threefold. And now, in the last talk, we were assuming F had log canonical singularities, but here we want to assume that F has canonical singularities. Okay, so to R, we want to associate a subvariety called the locus of R. And this is basically just the subvariety of X, which is swept out by curves that span the extremal ray R. So it's just the points in curve C such that the class of the curve C is inside R. So I guess a slightly, I mean, just a fact one has to prove is that loc R is a subvariety. And so there are three possibilities. So the first case is, well, possibly loc R is just all of X itself. Well, I claim that in this case, actually, R is KX negative, actually. And I guess this isn't hard. This is not hard to show. So I won't prove it, but somehow when we see the next case, you'll kind of see why it's sort of obvious. But the upshot then is that we can realize the KF contraction as a KX contraction, which, as Paolo explained to us in his first lecture, this is always possible. Okay, so the second case is that loc R equals D is a divisor. Now, as usual, we have two cases. Either D is invariant or it's not. So in the case where D is not invariant, well, I guess I'll leave this as an exercise. But basically, the proof is pretty similar to the case where D is invariant. So let's consider that case. Well, recall that we proved some sort of adjunction comparison theorem. So let's write KF restricted to D as equal to K of F, or I guess, sorry, so D is we actually know that K of FD is nothing other than KD, so it's K of D plus delta D. And let's write K of X plus D is equal to K of D plus theta of D. So recall from our last lecture that theta D is always less than delta D. And so in particular, you can check that this implies that R is Kx plus D negative. So in other words, so what we want to do then is we want to say that we can realize the divisorial contraction associated to our foliation as a Kx plus D contraction. But we have to check one thing. We need to check, or we need to control the singularities of the pair XD. xd. So I guess so. Maybe I just want to make an observation. This is an observation that I think a bunch of people have made. But the point is that if F has canonical singularities, then the pair xd has log canonical singularities. And so in particular, well, these singularities are mild enough that we can actually realize the log contraction. And so in particular, the kx plus d negative contraction exists. So I want to remark is that these two results give us the hint that we should try and construct the flip by constructing a log flip. That should construct AF flips by constructing log flips. Okay. So the final possibility is that lock of R is C a curve. And this is the flipping case. So we're going to have to take a detour really quick before we can explain how to construct the flip. And we'll have to introduce a new class of singularities that I promised you we'd explain. I explained to you guys last time. This notion of FDLT singularities. And the idea is that we can construct FDLT flips, but we're not exactly sure how to, at least I'm not exactly sure how to construct canonical flips in full generality. So, so definition. So let X again be a variety. F a codimension 1 foliation, or co-rank 1. I guess I'm flipping between the two. And we say F is FDLT if there exists a resolution to, so I guess a resolution to a foliation with simple singularities, so pi from x bar to x, such that, well, I guess 1, so f bar, which is nothing other than the strict transform of f, has simple singularities. In particular, x bar is smooth. So recall our definition of simple singularities from last time. So and 2, pi only extracts divisors of certain discrepancies. So if we write kf bar is equal to pi star of kf plus the sum of ai ei, or the ei's are all the exceptional divisors, then ei is strictly bigger than negative epsilon ei. So in particular, if all the ei's are invariant, then every discrepancy is strictly positive. Okay, so a bunch of remarks about this definition. So somehow this is, you should think of these as somehow being the next best thing to simple singularities. And somehow, I guess, and if you're coming from the regular MMP, they're a foliated analog of DLT singularities. We can also, there's also a variant, a version for pairs. But I suppose, if the interested, listener can work out what those versions should be. Another important observation is that if F is DLT, then the underlying space X is KLT. This is somehow an important fact. So somehow bounding the singularities of the foliation bounds the singularities of the underlying variety. Actually, we also could prove something similar, is that F being canonical implies that X is KLT. And I say this because here's a warning, is that canonical does not imply FDLT. So I guess the example to have in mind, even on a surface, is consider the foliation x partial x plus x plus y partial y. This is canonical, but not FDLT. Okay, another remark is that running the MMP, we always stay in the category. So running the MMP, starting with simple singularities, produces varieties or foliations with FDLT singularities. And then the final point, which maybe looks a bit funny, but we'll see why it's important in a second, is that let Z be a codimension 2 component of the singular locus of F. Then Z is contained in exactly, or I guess the Z is contained in 2 possibly formal invariant divisors. And this, so I want to mark this is actually a rather important feature of FDLT singularities, and this is what this is somehow the feature of them that we really need when we're constructing the flip. Okay, so the theorem so now let's return to flip. So the theorem I want to explain is that F DLT flips exist. Okay, so here's our setup. Well, let's let X and this Z, so X maps down to Z, and we'll call this, say, F. This is our flipping contraction. And inside we have C, and C is mapping down to a point P, which is inside Z. So this is our flipping curve. Okay. So let's let, I guess I should remark that, so C might have multiple components. But each component is tangent to the foliation. So let's let SI be the collection of all all invariant divisors meeting C. And okay, so the first fact, and this is essentially a result of Kano and Cerveau, says that if X hat is the formal completion of X along C, then we can extend each SI. So, I mean, a priori, SI is just a formal divisor in the completion of some point along P. But this result of Kano and Cerveau actually shows that we can extend SI to the entire formal neighborhood along C. So extend SI as a formal subvariety of X hat. And then a second fact, and this is where we really need FDLT singularities, is that KF minus, so maybe we'll do the hat, say we're restricting to X hat. So KX minus X hat plus the sum of SIs, this is FNEF. Or I mean, you know, it's NEF when restricted to, or maybe I should say we restrict it to X hat, and this is just NEF. I mean, so maybe, and so I guess I just want to remark is that this this requires FDLT singularities. Otherwise, I don't think it's true. So maybe just explain, you know, maybe the best way to explain this statement is just by drawing a picture. So let's say here we have X, here's C, and well, you know, maybe what happens is C is contained in the singular locus, and we have, you know, two divisors, you know, S1, S2 containing C. I suppose it's just sort of a straightforward calculation to check that. I guess so. Maybe okay. So the proof maybe in just as in one line is restrict to the strong separatrix. So I guess I haven't defined what the strong separatrix is, but for the experts in the audience, so restrict to the strong separatrix. In this case, using the notation as above. So sorry, delta D is bigger than theta D with equality at the generic point. A point of C. Okay, but at any rate, this fact right here, this is the place where we're using FDLT singularities. And so what we see is that in particular, Kx plus the sum of the SI, or I'm gonna keep writing hat, dotted with C is negative. Well, this is great because, well, we should now be able to construct the flip. But there are three problems. Well, we want to produce the log flip, but we don't know the MMP in the formal setup. This is our first problem. So, you know, we're working on a formal scheme, but we don't know the MMP for formal schemes. even in the specialized case. The next two issues, I don't really want to talk about them so much, but I just want to mention that they actually are problems that we have to contend with. So when we construct the flipping contraction, we only realized that we only constructed it by showing that Z was an algebraic space. But we need to show to prove that it's projective. And the third one is that even if we assume that x is q factorial, when we pass to the formal completion of x along a curve, the resulting formal scheme might not be q factorial. So x hat might, is not necessarily q factorial. So, I mean, these are largely technical issues, and I don't want to talk about them, but, you know, I just want to mention that these are things we have to worry about. Okay, so we now have this new question is, how can we produce a formal flip? Well, the idea is to somehow approximate the formal flip by somehow an algebraic flip, you know, a convergent algebraic flip, and perform that flip, and then show that this approximate flip actually gives you the flip that you wanted. So one quick remark is that producing the flip is a tall local on Z. So we can freely replace Z by an Étale neighborhood of a point. So we can neighborhood of P. I mean, okay, there's a bit of a subtlety here involving the existence of canonical models, but we won't get into that. But suffice to say that it's a totally local problem, so we can always shrink around a small neighborhood of P. Okay, so now here's the central technical ingredient. And it's a result of Artin and Nelkik on algebraic approximation. So this is just a corollary of Artin / Elkic approximation, which is a very classical result. So here's the statement. So it's a statement about local algebra, basically. So let AM be a Henselian local ring. And let A hat be the completion. And let's let M hat be an A hat module, and oops. And let's let S be a section on spec of A hat, global section of M hat, or I'll call it S hat. Now, suppose M hat is locally free on spec A hat minus the maximum ideal. So it's free on a punctured neighborhood of the point, or the unique closed point. Then for all integers n, there exists an A module M and a global section of the A module such that M is isomorphic to, or sorry, whoops, M tensor A hat is nothing other than M hat, and S is equal to S hat mod MN. Okay. So just scroll up so we can look at it. Okay. Great. So how do we use this? Well, let's let let's see here. So let's let A hat be the formal completion of the local ring of O of ZP. And observe that we have a map X hat to spec A hat. I guess I'm doing a bit of a cheat here, but it's not so big. And we'll call it, and I guess we'll call this F. Now consider, now let's let M hat be equal to O of F star SI. So this is a reflexive sheaf. Well, but it's a bit better, right? Because SI, so SI is a Cartier divisor, or is a Q Cartier divisor on X hat. And this morphism F is an isomorphism away from P. So what we see is that, so SI is Q Cartier. And so this implies that O F star SI is Q Cartier away from P. But this is perfect, right? So, I mean, and I guess cheating a bit, it's not such a big cheat. That we can assume actually that O of F star SI is locally free away from P. But that's perfect now, because that means so if we let A be the Henselization of OZP, this implies that there exists an M on spec A such that M tensor A hat is O of F star SI. And even better, there also exists an S in H0 of spec A of M such that S approximates the tautological section. Section of O of F star SI. But the next observation is that Henselizations are local rings in the Étale topology, are the local rings for the Étale topology. So this implies that there exists an automorphism. So there exists z prime to z tall and a reflexive sheaf M prime on Z prime and a section S prime, which give M S in spec A. Okay, but the point is that the choice of a reflexive sheaf and a section is nothing other than an effective divisor. So what we do is we let S tilde I, we define this to be equal to S prime is equal to 0. And we can check that this divisor, this approximate, or this divisor, so I guess it follows that that S tilde I is equal to SI mod MN for some N very big. Okay, so the idea now is that we construct, so we've somehow approximated all these formal divisors by global algebraic divisors on some Atala neighborhood. So let's let X prime be equal to X cross Z prime, and we can construct the kx prime plus S tilde I flip. And I guess what you can check for all n sufficiently large, this flip is independent of the approximation. All our choices of approximation. And so gives the KF flip. Okay, great. So yeah, that's how we construct flips. So again, the hard part is that we really wanted to construct a formal flip, but we don't know how to do that. So we just approximate this formal scheme by some other algebraic scheme, and for which we know how to construct the flip. Okay, great. So I have a few minutes left. So I think Roberto might talk about termination. So I don't, just in case, I don't want to go too far into termination, but I just want to maybe just list out two ingredients, and then maybe just as a teaser in case Roberto decides to talk about it. So so the first thing is to show that flips become disjoint from LC centers. So somehow we show that flips eventually they become disjoint from the worst singularities of the foliation. And then two, we used Bott's partial connection. To show that so terminal KF flips KF flips are actually KX flips. And so somehow then we can apply three-fold termination. Okay, so the last thing I want to talk about, maybe because Paolo mentioned this, is the base point free theorem. So here's a rather remarkable fact, is that the base point free theorem is false for foliations. In particular, it's not obvious how to construct canonical models for foliations. Which is something we'd really like to be able to do. However, there is one case that there's a version of the base point free theorem that Paolo and I were able to prove, which seems pretty useful. So I just want to state it here, and then maybe that'll be it. So let's say F delta is an FDLT pair, where delta is equal to A plus B, where A is ample and B is effective. This is much stronger than just saying delta is big, or that there's a big boundary. But that's just a technical point. A simple example of this happens, say, is that, like, F has simple singularities, and delta equals A is ample. So in this special case right here, the base point free theorem holds, but it's really a more general fact. And let's suppose that KF plus delta is Nef. Then KF plus delta is semi-ample. Okay, the proof is, I guess I'm running out of time, so I won't explain much about the proof, but the proof is basically a consequence of, follows from the cone and contraction theorem on non-Q factorial varieties. And again, this is somehow not such a crazy generalization, but it is a rather technical generalization. But once you have a cone and contraction theorem for non-Q factorial varieties, I guess I should also mention, and a canonical bundle formula. That's important too, for fibrations. So once you have these two ingredients in place, it's kind of simple. Okay, but yeah, like I said, in general, this kind of statement is false, and this is, I think, is a good question to figure out how to get around this problem and how to deal with that. Okay, cool. So I think I'll end there. Thank you.